Well, this is gonna be a relatively long one, so I might actually have to break it into two pieces. But the objective here is to really introduce you to the a bigger world of finite element modeling, and then to illustrate that everything that can be done fundamentally we have been talking about is to develop an element using principal virtual work, and then assemble those elements, apply boundary conditions, solve them, and do post-processing. We're gonna illustrate this with a simple 2D element, but in general we're gonna just do a little bit of introduction to the finite element method. Okay, finite element method, I mean, yeah, you guys are all seniors or graduate students. If you don't know it by now, then yeah, God help you, But basically we've covered quite a bit of it already in this class. We have the line element. So that means that's our typical a 2D bar. We have our beam, we have our frame, and those actually consist of a good portion of what we use in civil engineering or structural engineering. Yeah, a good portion of it. Then we have the planar, always just say plane element. So in this one we have plates and shells, and then those are, if you think about them, they are just like triangle stuff. There are some differences, right? The plates, they might only have in plane degree of freedom, but really the shells, they can do out of plane bending and deflection. If you just pick up a finite element program, try to model some floor or whatever, just go with shells, because you do want them, although they are plane, but they can do 3D stuff. Then finally we have those solid element. Those are people like to think of them as blocks, but the simplest you can get is a pyramid, so it's something like that. Then those are, we call them bricks, or 3D solid, and it's that. Then the finite element, this is just element types. Then they combine them, every single one of them, they can be combined with different materials. And then those materials, they can be linear, and then nonlinear, of course. And then there's a whole bunch here. Yeah, if you do this, there's so much more here. Then you combine your geometry with a different material, you have all kinds of crazy elements. And within those, we slightly touched on the beam when we talk about in this class we mainly talk about Euler-Bernoulli beam, because we use a Euler-Bernoulli displacement assumption. But yeah, frankly, you can use different displacement assumptions, like Euler-Bernoulli beam. Then you can have a Timoshenko beam. That's just another different displacement assumptions. That's why when you see ANSYS or Abacus, those pretty advanced FEM software, they don't just have one beam or one frame. They have beam 102, beam 503, whatever. They actually run out of names. But if you look inside their user's manual of that element, you'll be able to see what kind of things you're really getting. yeah, which kind of displacement functions are using. But with that aside, let's talk about 2D element just as an example for now. So if you really follow the introduction, why are we doing this? So we've done bars and beams, we can do trusses, we can do frames, but we're really trying to say, okay, if you have a even in structural engineering, you have some like a deep beam, which is like a beam that's actually not like a beam, it's like a plate, and then you cut some holes in it, and then you add a force to it, and then you're gonna say, okay, what's the deflection? Okay, and then also what's the stress inside it? I mean, do you know? The solution that provided by 2D element is really just say, okay, well, we like even for a thing like this, you're probably not gonna be able to find a closed form solution, so we will solve it numerically. What we'll do is that we will start to kind of dissect this thing into a lot of elements. And then we'll just do this, and then we'll dissect into like triangles and everything. Yeah, you got the idea. I mean, when it's like here, you just try to approximate with triangles. Yeah, you can use like smaller triangle, just try to kind of refine the mesh here. But by the end of the day, if we can establish a element that is 3 nodes, triangle at I, J, and K node, and then if we can do a shape function, we can do internal stress and strain using the serial infinitesimal string, and then we can get the EK, and then we can assemble this entire thing. Now then apply the boundary conditions on those nodes. And then we can be able to solve the deflection on these nodes, and also we can know all the stresses and strains inside this body. So that's the idea. So the example we're going to do in this case is called constant. Yeah, people sometimes they call it constant strain triangle. And then you will know why it is constant strain in a little bit, but let's set it up. Okay, so basically it's a 2D element, so it's in 2D, x and y, and it only moves in 2D, okay, it's not gonna go 3D. And then it has 3 nodes, and then basically we'll name them I, J, and K, okay? And now we'll worry about a point P inside it. It has XP and YP as its coordinates. Then we're gonna say, can we find a function? It's 2D problem, so the P can move in 2 directions. So UP, okay, and the VP. Can we find a function that of the x and y? That if we plug in the P as coordinate in there, it's gonna give me how much it moves. Then you're like, yeah, probably, but I need to know something, right? I probably just out of the tradition of finite element, I probably need to know how much IJK moves. So if I know U and V movement of node I, J, and K. While we're doing that, we might as well just say, okay, for this element, although we don't know how to do it right now, but it is likely the delta vector for this element, when everything said and done, will be ui, vi, uj, vj, uk, and vk. Okay, and then corresponding is, then you have the element force vector. That would be the force in ix, force in I in y, force jx, fjy, and fkx, and fky. Okay, and then we just need to find a ek that's corresponding to it. Then we're going to also assume, like material, we're not going to go too crazy on this. It's just going to be isotropic. Yeah, you guys know what isotropic means? Yeah, well, it's kind of it's the same everywhere. It's controlled by the elastic constant E and Poisson's ratio V. Gee, I think it's gonna be some confusing when we have like the displacement as V and the Poisson's ratio, but I mean this guy's not used that much. I'm gonna try to be a little bit cursive on that. So Poisson's ratio. Okay, so yes, step one is always displacement functions. So this actually is like a general understanding or assumption of how, if I move ijk around, wiggle it around, how this thing gonna deform mathematically. So we need to kind of go by this. Basically, if I know the ijk displacement, then can I find p's displacement? This p being anywhere within it. So we'll say the thinking is that, okay, let's not mix those two guys up, because first of all, we need to assume that when j moves this way, k moves this way, I moves this way, they don't move in the y direction. Nobody moves in the y direction, then the p will not move in y direction. Then vice versa, if everything is just moving in y, then the p should not move in x. Otherwise, it will be weird. Okay. It could actually happen. I'm not saying that it could not. Say if I don't move too much, but k moves a huge amount, j moves a huge amount, there might actually be some like a rotation, like on the p. Then the p could actually go closer to I a little bit. But those are in the realm of large deformation mechanics. Yeah, theory of infinitesimal string, if the movement is that large, it actually won't work. Then there might be some correlation between those two, but for our case, it's small displacement, it should be decoupled. So whatever we did on the u, how we formulate it, it should also be exactly the same as in v, because I mean you can't distinguish which one is x and y if you just look at the element. So let's focus on the u, the x direction. So the question is like, if I know ui, uj, and uk, can we find up? Okay, then we're like, okay, then yeah, we'll just assume now we're working in 2D now, so we can't just do ux. We actually have to do uxy. That equals to, like, what can I do? I just say a1 plus a2x plus a3y. That's the simplest I can get. And it's a good cue that it might work, because why? Because now I have three unknowns, a1, a2, and a3. And I know three conditions. So, which means I can have this type of equation. I can have just plug in the nodal location of I, J, and K, this thing should work, right? So I could have like U xi and yi equals to a1 plus a2 xi plus a3 yi should be equals to ui. And yeah, then you know the drill. I can do the a1 plus a2 xj plus a3 yj equals to uj, and a1 plus a2 xk plus a3 yk equals to uk. This is a little bit counterintuitive, because when we write things like that, we say, okay, we're going to solve for x and y. But in this case, the x, y is what we already know, because when you draw the element, you already know where I, j, k is. What we're trying to solve is a1, a2, and a3. So what we're actually going to solve is a equation or a matrix or linear equation like this: 1, 1, 1, xi, yi, xj, yj, xk, yk times a1, a2, a3 equals to the known displacement u1, ui, uj, and uk. I mean, you could think about this as v to be the same, exactly the same. Okay. So the questions like how do we actually solve it? I mean, there's a lot of ways to solve it. In fact, like I said, in MATLAB there is a symbolic computation toolbox. You can actually put in symbolic matrices and then do the inversion and all there. But everything said and done, I'm just gonna give you the answer, and you know it's solvable. So basically, we solve for a1, a2, a3. Okay, you solve them, and then you plug back to the u x, y equals to you know, a1 plus a2x plus a3y. And then, yeah, I'm not gonna do it, but because it'll be a mess. But you can do it if you have a big enough paper, and then you have a lot of time. You can do this, and then you have to rearrange. So you're like, okay, rearrange what? Oh, guess what? Because this equation, you have x coordinates, xy coordinates of the three nodes as known, and then you can also have their displacement as known, right? So the solution in a1, a2, a3 will have those guys and those guys. And then what we're going to do, like we're going to always do when we try to derive the shape function, is that we're going to regroup this guy after you plug back in all the solutions. We're going to regroup them in terms of ui, uj, and uk. Rearrange, we'll see in terms of yeah, basically whenever a term that contains ui, we're going to put them in there, uj and uk, and then we're going to rewrite it in a way that is u x y equals to ni, which is the function of x and y, and ui plus nj uj plus nk uk, and then nj and nk, they're all a function of x and y. In fact, if you just follow that, I'll just give you the n equations. 2a over ai plus bix plus ciy. Then you're like, hey, hold on a second, what are those? And what's a? So basically, let's see where a is the area of a triangle. Okay, then you're like, how do you get that? Oh, yeah, if you really do this, and then you find out that magically it just comes out. Then you're like, what's ABC then? Okay. AI, that's the kind of exactly the reason I don't write this thing out, equals to xj yk minus xk yj. Wow. Then bi equals to yj minus yk, and then ci equals to xk minus xj. So basically those are the known coordinates of the nodes. You basically do that to calculate those numbers, then plug them in back here, divided by the area of the triangle, you got this. Yeah, again, you're like, how does that all work? I mean, like I said, if you have an afternoon to kill, solve for A1, A2, A3, plug it back in, real unit terms, and then you're gonna get this. Okay. Then apparently nj equals to 2a of aj plus bjx plus cjy. Yeah, I just say aj equals to x. Then yeah, here the sequence has to be right. xkyi minus xiyk. You can't flip it, you know. Yeah, you're like, okay, I know, yeah, I is something j and k, but yeah, if you put this thing on top, then yeah, you totally mess it up. Okay. Then bj is yk minus yi. Cj is xi minus xk. And then, yeah, you know what's coming. ak plus bkx plus cky. Okay. Then ak equals to xiyj minus xjyi. bj is yi minus yj. ck is, yeah, this is extremely easy to make mistakes. xj minus xi. So the bottom line is that if you know the coordinates of nodes I, j, and k, generating the n's and the u, x, y is not difficult. Yeah, deriving them is probably pretty difficult, but if you know all those numbers, you just plug them in, and then the n's are just the linear function of x and y. So we'll say similarly, you can get your v x y equals to ni vi plus nj vj plus nk vk. Like if you kind of look back when we like derive this whole thing, if you just replace u with v, everything will be exactly the same. So that's why the same shape function will also apply for v. And I think I'm gonna stop it right here, but before we go, I'll show you how the shape function actually look like. We all know x, y, and z or whatever. We'll just say, yeah, z. We all know that in a 3D plane, if you 3D space, if you have a function that is linear to x and y, what this thing represent is actually a plane. So the although there's so much derivation, but the physical concept of this is so simple. Basically, if this is I, the ni plane is simply something like this. If this is 1, this plane, that's the ni xy plane. Yeah, so basically, yeah, it's like you keep other two guys constant, and then just move this up by 1, then that's the deformation if you move I. Yeah, so you got the drill. I mean, I'm just gonna draw another one just for fun. Y, X, just try to do a decent job. Yeah, guess what's if this is I, this is K, this is J. Yeah, you know, this would be your this will be your nk plane. Got it? Yeah, in fact, it's very intuitive. Okay, well, we'll stop right here, and then yeah, we'll continue on the next one, because yes, it's close into 30 minutes.